Hi everyone, welcome to an exploration on z-test, a fundamental tool in inferential statistics. Z-test is a method to determine whether there is a significant difference between a sample and population means or between the means of two samples, especially when the sample sizes are large and the population variance is known. There are lots of applications extensively used in the field of psychology and medicine and social sciences. Let's then get started with Z-test, understand how it is designed and how we can implement it using Python. So a little bit of Python programming knowledge would be handy, and essential statistics like probability concept, distribution, standard normal distribution, Gaussian distribution would be really useful here. So what is z-test? It's a method to compare two population means if they are same or different, especially when the population parameter, which is a standard deviation or a variance, is known in advance. And the samples are exhibiting normality in the distribution. Particularly useful when the sample sizes are large, let's say more than 50 or 100 or even like 200 or 300. Assumptions for z-test is normality, so population from which the samples are drawn should be normally distributed. For large samples, the CLT or central limit theorem will allows the z use of z-test even if the population is not normally distributed. Because with a large number of samples, the sample parameter will tend to have a normal distribution. Another assumption is the population variance should be known in advance. The sample should be independently drawn from the population, and the size of the sample should be large, uh, definitely more than 30. And the sample variances should be equal or similar to each other, just like we had in t-test as well. So one sample z-test, where we're talking about one sample, so that particular sample's mean and the population mean subtracted and divide by standard error. And that gives you a metric or a z-statistic here. Similarly, for two sample z-test, we have two samples. So we take the mean of both the samples, x1 bar, x2 bar, and the mean of the population 1 and the mean 2 of the population again. Again, the standard error in the denominator. So this is going to give us the statistic that we can use to compare against the critical value. Another variation of z-test is one sample proportion z-test. That means you have a sample and you also know the proportion. So take the proportion and subtract it in the numerator, then the standard error. One more flavor of z-test is when we have two independent samples and the proportions of each one. Now, all of these formulas are inbuilt into Python implementation. You may want to do manually, or you can use the Python packages to conduct a proper, flavor of the z-test. Let's see some examples of z-test. One sample z-test, testing if the average height of sample differs from a known average height of a population. Of course, the standard deviation should be known. Two sample z-test, again comparing the average test scores of two different classes to see if there is any significant difference. Again, we need to know the standard deviation of the population. Same with the proportion. For example, here the proportion of the defective item in a sample, let's say you anticipate 10% of the product to be defective, and that's the known parameter. And then you can check if the proportion, whatever proportion that you have in the sample, is differing or similar or not similar to the proportion of the items in the population. And likewise, you can also have two sample proportion z-tests. So we have like, two fractions, let's say male and female in a sample, and the percentages or proportions are zero point 0.3 and zero point 0.4. So then we can compare that with the population proportions. So let's compare the z-test and a t-test. The sample size in a t-test is small. Sample size in a z-test is larger than 30. Population variance is not known in t-test, but it is known in z-test. Distribution is normal distribution in a z-test, but it is a t distribution in a t-test. And the use cases are same, just that in the z-test, we know the population standard deviation. In t-test, we don't know that. So assumptions are also pretty much the same. The population variance is known, which is not the case here. And large sample size and the small sample size and the normality condition holds here. Critical values are derived from the standard normal distribution for z-test is derived from the t distribution. Degrees of freedom is not required in z-test, but if you remember, we talked about it in the previous lecture. On t-test, we use degrees of freedom in t-test. So applications are to check the sample mean in both the cases, but z-test is applicable when we have a large sample size and known population variance. P-value calculation is called, statistic is used to compute the p-value, and here t statistic is used to compute the p-values. So let's see some example here. And here the mean score of students in a class is greater than 82. The teacher is claiming that with a standard deviation of 20. And then we collect some sample of 81 students. We can check if the mean score of 90 is then we can use against the population standard deviation and see whether that claim is true or not. We'll try to implement this in Python. Okay, so here is the problem statement. The teacher claims that the mean score of the student in the class is greater than 82. So that's the claim with a standard deviation of 20. And if the sample of 81 student was collected with a mean score of 90, now we can compare with the mean of the population and standard deviation, and let's see whether that claim is true or not. So we're going to use the SciPy package here, and the population mean is 82, and the sample mean that we collected is 90, and then the population standard deviation is 20. And the sample size is 81. The alpha, we take it as 0.05 as the level of significance. The null hypothesis is the mean score of student is less than or equal to 82, and the claim is greater than 82, so that will be our alternate hypothesis. So let's describe the z-test or z-statistic, sample mean minus the uh, population mean divided by the standard error. So we'll put these values and we get the z-statistic of 3.59. And the critical value for given alpha can be computed using the percentile probability function of a normal distribution. That's 1.64. So this 3.59 is more than 1.64. So apparently this is a case of rejection. So that claim is not true. So you can verify this by using the p-value also. The p-value can be computed using the cumulative density function for the computed uh, z-stat here. And then we have a p-value which is 0.0001. That means it is lesser than the null, which is lesser than the significance level. So we can reject the null hypothesis, and that means uh, the claim is not true. All right, so now we can plot it here. and you see the statistic is way outside the rejection region. That means, or way above the rejection region. That means you can reject the null hypothesis. The null hypothesis is the mean is less than equal to 82, which is not true. And that means the claim that it is greater than 82, that holds true based on the data. So we're going to reject the null hypothesis. All right, so that's the straightforward implementation of z-test. So why we take the approximation of a normal distribution? Because we are talking about a large number of samples, and for large number of samples, the central limit theorem applies, and the approximation is that it will occupy or it will take a shape of a normal distribution, and that is why we use a normal distribution in case of a z-test. I hope you like the presentation, and we'll see you in the next lecture. Thanks for watching.